Welcome to Black Hat Briefings, held November 21st through the 22nd, 2001 in Amsterdam. This is videotape number 12, How We Beat the 5th Argus Hacking Contest.
First of all, I would like to welcome everyone who has come to our presentation. It will be about kernel level vulnerabilities and the possible impact that they might have for the security of operating systems. And the whole presentation will be performed upon the context of the 5th Argus Hacking Challenge. My name is Adam. These are my two colleagues, Michał and Sergiusz. We are from the last stage of the leading group.
A little bit higher.
Sorry? Higher, the microphone? Volume. Okay, is it yeah? I don't want to keep it too close to my mouth because it's worse. So first, let me tell you a few words about ourselves. So we are a non-profit organization which has been established in 1996 in Poland by a group of computer enthusiasts. We conduct research activity which is not associated with any commercial company. We have, from the very beginning, 4 members, and we are all graduates of the computer science schools from the Poznań University of Technology. For the last couple of years, the 6 years actually, we've been all working in the same company, and that is Poznań Supercomputing and Networking Center. We've been working there as a security team. I guess that most of you who knows us from the proof of concept codes that we publish on our websites, but this is not the only field of our activity related to the security field, because apart from continuous search for vulnerabilities, we also try to analyze different available security solutions and to create some defense methodologies or some new methodologies for attacks. We also develop various tools for reverse engineering and penetration tests. Unfortunately, they haven't been published yet, but I hope that in a couple of months they will be. We've been doing some experiments with distributed host-based intrusion detection system, and that is also able to provide active protection capabilities. So, coming back to the presentation itself, first I will give you all a brief introduction to the Pitbull Foundation intrusion prevention system. I think that it could be a good start to the topic of a challenge itself and the way how we hacked the Pitbull and won the challenge. It is also here because we wanted to show you the strength of this system, its protection capabilities, and that in fact it wasn't so easy to hack the Argus challenge. Then I will tell you a bit about the challenge itself, reveal some of the information from behind the scenes. Later, LDT kernel level vulnerability will be discussed. This was the one that let us win the challenge. And we will present you a reconstruction of the events that took place on that night when we attended the challenge. At the end, the second part of the presentation will give you more technical details about the vulnerability and the way that a proof of concept code for it had to be written. So as for the motivations, in general, as I said, this presentation will be about kernel level vulnerabilities, its exploitation, and a possible impact that they might have to the security of operating systems or any enhanced security products. As you know, Argus Pitbull Foundation was a flagship product of Argus Systems. It was it was given several security certificates and it was awarded with several prizes. What is important, it passed ITSEC B1 evaluation criteria, and it was acclaimed as an unbeatable system. So what we would like to show you through this presentation is that maybe there isn't such a thing like a 100% secured system, and that the system can be considered secure only in a specific place and at a specific time. So a few words about the Pitbull Foundation itself, what it is and what it is able to provide. So Pitbull is a software enhancement to the operating system, and it is based on the trusted operating systems technology. It is installed as an upgrade to the operating system, and it is integrated with it at the operating system kernel level. Pitbull got B1 security evaluation criteria. It passed all the tests that are required to obtain that criteria. It was also approved by NSA, DoD, NASA for governmental use. And it is in general recommended after the tragic events of the September 11th. It is recommended by NSA and DoD for security purposes, for securing networks and computer systems. And of course, before the 5th hacking challenge, it has never been hacked before. And as it was stated on the Argus Systems site, there are about 5 million attack attempts to hack the system. So let me tell you something about Pitbull features. It is security enhancement to the operating system itself, and one of its main tasks is to fill the gap that is present in standard Unix operating systems, the gap that allows super user do everything with the system. So Pitbull tries to fill that gap to eliminate some potential threats to the security. It completely removes super user privileges. It also implements some of the features that are common to trusted operating systems, like mandatory access control and information compartmentalization. On Pitbull, it is possible to control the flow of information within the system. It is possible to control what kind of information can be put into the system and whether it can be obtained from the system. In Pitbull, administration tasks are divided into several roles, administration roles, and as it was said before, it operates at the kernel level, so it protects the system where that such protection should be in fact applied. It is not a user level solution, but a kernel level solution. I will try to, on the next few slides, I will try to give you some deeper look on the Pitbull features. So, as for privileges, in standard Unix operating systems, whenever a program needs to do a privilege operation in a system, it must be given a set user ID bit access right. So, and of course, it poses a great security risks. We know that from the past and experience, and from what is published, what has been published through different security mailing lists with regards to the different security vulnerabilities. Pitbull eliminates the threat by dividing the root user privileges into many sub-privileges. So there isn't such a thing like one super user in the system. This feature is very similar to capabilities mechanism. And in Pitbull, there are such privileges like separate privilege for mounting file systems, for accessing proc file system or devices. Having the possibility to deal with privileges, we can apply on a Pitbull system the least privilege principle, which says that a process or executable should only have the minimum necessary privileges that are required in its operation. Also, because of the authorizations and roles that are distinguished in the system, we can separate the role of the root super user into several different roles that are needed in administration of the system. What I can also say is that by appropriately applying privileges and the least privilege principle, we can enable privileges within a very specific time period of a given program execution, and only for the time when it really needs that privileges. Pitbull also introduces something that isn't very common in standard Unix operating systems. This is information compartmentalization. This feature is very closely related to the MAC access control mechanism. In standard Unix operating systems, access control is done with the means of permission bits and ACLs, that is discretionary access control. On Pitbull, access control is always mandatory. So even if a user has access to a given object according to the DEC access control, he won't be able to touch that object if it is not clearly stated by the MAC mechanism. And of course, because of those mandatory access control restrictions, MAC always overloads the root-owned process because root isn't a power user anymore on the system. So whenever an access on a Pitbull system is made to an object, whenever a subject tries to access any object, there are some rules that must be okay. So every object on the system, including files, directories, devices, inter-process communication, network devices, every process on that system has a feature that is called an attribute that is called a sensitivity label. Sensitivity label is composed of two components, a classification and compartments, where classification is a hierarchical component of sensitivity label, and it defines the actual sensitivity of the information. For example, we can have a classification public that states for publicly available information, or we can have a classification top secret that defines the information that shouldn't be available for everyone, just for a limited amount of persons. As for compartments, they are non-hierarchical components of sensitivity labels, and they define sets of information categories. For example, we can have compartments that reflect a group of people that should have the access to the same category of information. On the next slide, we have a picture that presents the information compartmentalization, a sample information compartmentalization model. Here we can see two compartments, accounting and management. Each compartment contains objects that can have public access to that information contained in this compartment, or restricted access. What is important here is that none of the objects that are in a counting compartment are unable to access management compartment. That is impossible. And also the public objects with public accounting sensitivity label can't access restricted accounting objects, as restricted has higher classification of information, but restricted accounting can access objects with public accounting sensitivity label, as restricted is higher information classification. There is always in Pitbull there are always two labels, sensitivity labels appropriately for the lowest classification of information, that is implementation low label, and there is always the highest information label, that is top secret all. Top secret all label, possessing that label allows to access any information on the system. So there are some rules that, an example of rules that must be fulfilled in order to access objects in a Pitbull system. These rules are closely related to the mark mechanism and to the sensitivity labels. So whenever a subject wants to access an object in the system, for example, for reading, the sensitivity label of the subject must dominate the sensitivity label of the object to which the access is attempted. Also, a process cannot open any file for writing. Write access is only obtained when sensitivity labels are equal. So possessing a sensitivity label that is greater than a sensitivity label of the object to which the access is to be gained, that is not enough to get the right access to that object. And of course, processes are not, by default, are not able to change the sensitivity labels. This can be possible only if appropriate privilege is possessed, but that is not enough because also an authorization must be issued to a user who wants to change his sensitivity label. So when it comes to role compartmentalization or authorizations, as I said before, there is no such thing like a root superuser on the system. Its tasks are divided into several roles, and whenever a privilege operation must be taken in the system, a proper privilege is required, but also according to the implemented to the Pitbull implementation, also an authorization must be obtained, because authorization is required to use a privilege. And having both authorizations and privileges, we can distinguish different roles in a system. For example, we can have system operators that are only capable of creating backups of the system, and etc. If a user is not authorized for a privilege, he will not be able to execute any file that owns such a privilege, because he always needs proper authorization for that purpose. And the last, I think, the most important feature of the Argos Pitbull is it's the fact that it is operating at the kernel level, and that all decisions are made at the operating system kernel level. All decisions with regard to the security of the system. So, because the kernel is one of the best written part of the operating systems, and because it is one of the best protected parts of the operating system, it is a good way of protecting operating systems, because there isn't any combination of user level or application level security that would provide such a level of security as a kernel level solution. What I could also say here is that because of that, the Pitbull operates at the kernel level, and the fact that user ID 0 is an average user in the system, root exploits are no longer useful to intruders in a case of Pitbull Foundation. So on the next slide, I will give you a few comments about this product, our comments. In general, the whole idea of the product is quite good. We really liked it because it is very similar to the software that we implement, the intrusion detection and prevention system. We think that this is the only way to provide strong security to operating systems. The only way is to implement any solution at the operating system kernel level. What is also a plus of Pitbull Foundation is that it is based on trusted operating systems technology, which is also based on proved mathematical security models, and that it protects against classical user-level attacks. But of course, it also has some disadvantages, as some new approach to security. It is also potentially open to some new threats. In our opinion, some of its features seem to be overused, for example, privileges. And from our experience, we think that securing any system with Pitbull Foundation is really a difficult task. It is very difficult and requires a lot of experience and work. So that would be all as an introduction for Pitbull product. Now we'll come to the presentation part that would be telling more about the hacking challenge itself. So the 5th Argus hacking challenge took part in April this year, and it was coincided with InfoSecurity Europe 2001 exhibition, which was held in London. The rules were pretty simple. There were one system. People who attended the challenge were supposed to hack that system. It was secured with Pitbull Foundation 3.0 MO4, and it was servicing two fictional web pages of. It was servicing the web pages of two fictional companies, X-Type and XCURSION. The rule was to hack the system within 5 days' time, and of course, in the case of success, the winners were supposed to reveal how that was achieved, and for successful hacking of the system, a price of $50,000 were supposed. So this time, on the 5th hacking challenge, there was one system that was supposed to be hacked. That was Solaris 7 on x86 platform. It had Pitbull Foundation 3.0 and Compact web appliance product installed on it. It was partially secured. It had some patches applied. Of course, it had some services decreased and some set user ID bits removed from it. We've seen Argus guys visiting our web page and downloading all the Solaris x86 exploit codes a few days before the challenge. As an access to the system, a trusted SSH service was provided. There was also a public webhook account available with a shell access to the system. The system was configured so that user webhook as well as HTTPD server, X-Type and XCURSION web pages directories were put each in a separate compartment. And also we noticed that in the system there was some advanced security network rules applied for network protection, so it wasn't possible to establish connections from within the system to its outside or to bind to perform any socket operations like bind, for example. This is a simplified configuration of the system that was put to be hacked. We can see here that there are two compartments, X-type and XCURSION, with appropriately restricted X-type sensitivity labels. Both compartments were put in separate. Both web pages were put in separate compartments. So an access to one of the web pages didn't grant access to the other one. There are also another compartment that were provided for the webhook user, and it was assigned a public webhook sensitivity label. Of course, the webhook user didn't have access to any of the X-type and XCURSION compartments because all these compartments were disjoint. Not only because the classification of the sensitivity label was the lowest possible, that is public. And here you can see the web page that was provided for one of the companies, and also the original web pages, and also the web page of the second company. The whole content was prepared in a quite nice way. I mean, the pages were pretty nice. These are only the entry pages. And coming to the LDT bug, as you probably know, we used the LDT bug to win the challenge. We thought that this is the only way to break the Pitbull protection, as we were aware that any user-level root exploits didn't give a chance to succeed. And LDT bug at the time of the challenge, gave us the possibility to execute code at the kernel level, and possibly a way to bypass Pitbull protections. And what should be also mentioned here is that the proof of concept code for the LDT bug was very uncommon and tricky to write, but that would be presented further during this presentation. And what should be also said about this bug is that we didn't find it. It was first published in the NetBSD Security Advisory in January this year, and it was reported by Bill Sommerfeld. According to the advisory, Solaris, NetBSD, and OpenBSD systems were vulnerable to it. We verified that Solaris x86 is vulnerable. We also found the existence of this bug on SCO Unixware and SCO Open Server. We contacted with the vendor and informed them about the fact. At the time of the challenge, Solaris x86 was vulnerable, as well as Pitbull was vulnerable. And after the challenge, there was some discussion whose fault it was. Of course, it was a Solaris bug, but Pitbull, as a security enhancement to Solaris operating system, should also protect against such vulnerabilities. So in our opinion, it was also Pitbull's bug because it allowed an average user to call an LDT syscall, and that was a threat that wasn't protected in any way by Pitbull. In the next few slides, we'll try to give you to show you a reconstruction of the events that took place that day when we attended the challenge. We hacked August Pitbull within 24 hours time, constant work. During that time, we of course tried different ideas. We were making some mistakes, but fortunately none of them led to the boot of the system, as this could be treated as against the rules of the challenge. So we attended the challenge at 9 AM Friday. We found information about it in one of the security news portals. we've installed a Pitbull 3.0 MO4 system on our local machine for the know your enemy purposes, we can call it. We wanted to get more familiar with the system, as we had only before we had only little access to it. We downloaded the Pitbull Foundation from the Argus Revolution website a couple of months ago, but didn't have a chance to look at it into deeper. We just simply got interested in that product as it was very similar to the solution that we are developing. So after installing a Pitbull, we tuned the system configuration so it reflected the challenge rules the best as it was possible for us. We also verified the existence of the LDT bug on our testbed system. We used ADB kernel debugger and disassembled a kernel procedure system call and saw that that system call wasn't protected by Pitbull in any way. And in phase 0, that we call it, we also developed a fully operational proof of concept code for LDT bug, as we only had a skeleton that was able to crash the system. And that phase 0 took us about 9 hours time. Sorry. We had 2 teams of 2 people. One of them were working on a Pitbull configuration, the other one was working on the proof of concept code. In the second phase, we logged into the webhack account with the use of SSH. You can see some of our commands that we issued at the beginning. That was simple verification of the privileges that we had. We see that we were webhack user in a webhack group, that our sensitivity label was set to public webhack. We were able to read PES-WD file, and we noticed that there were 2 users appropriately for Xtype and XCURSION web services. We didn't have access to the home directories of the web pages for these companies, and we couldn't also create any files in these directories. So that was a first look around in the system. We also verified the existence of the bug on the system, but we are not going to show you here how we did it because of time pressure. This slide presents in a brief way the goal of our hack. We wanted to get access to the index HTML file of the Xtype company. That file was protected with a MAC mechanism, had restricted Xtype sensitivity label. It was also protected with a DAC mechanism, had read and write access to owner of the file and read access to others. We were of course unable to get access to this file at the beginning of the contest, as user webhack was put in a separate and different compartment. That was a webhack compartment, and according to MAC rules, webhack and Xtype compartments were disjoint, so we couldn't get access to any objects in this compartment. So read and write operations simply failed. In the next phase, that was about 20 in the evening, we applied our proof of concept code for LDT vulnerability that was written during that day. We assumed that it would give us nothing, as in Pitbull, root means nothing. It is an average user. We gained root user privileges, and we were trying to play with the privileges. Of course, nothing changed apart from the user ID. We didn't have access to any web page directories. Our security label was still the same. We also didn't have access to the etc security directory where the configuration of the Pitbull Foundation was kept. And our accesses to Pitbull configuration files and web pages of the fictional companies simply failed because, again, our compartments were different. So user webhook was in a different compartment than a target object to which access was attempted to be gained. We only had root user account, root user ID, but that meant nothing for Pitbull Foundation. The next phase, an hour later, we already knew that the web pages are protected with the use of some kind of the mechanism. So we decided to change our proof of concept code and to set its classification component to top secret. And as you can see, after executing the exploit code, we got top secret classification component in our effective security label. But still we didn't have access to web pages of the target directories. We also were unable to create any files in these directories. And why was that? You can see that we had root user ID, our sensitivity label, its classification component was set to top secret, but we were still in the same compartment. We didn't change our compartment. We were in the webhook compartment, and it was still disjoint with a target compartment to which we wanted to get access to. That's why read and write operations simply failed. So in the next step, we decided to change not only top secret not only the classification component of the sensitivity label, we also changed compartments and set it to all. So we wanted to obtain the highest possible information in the system. And as you can see, after that, we were able to read configuration files of the Pitbull itself. We obtained read access to these files. We were also able to read the www directory. We could change directory to the target directory where we wanted to change the web pages. We could see those web pages, and at this time we thought that it was possible that it was all, but unfortunately we're unable to write to the files. We could read them, but we couldn't write to them. And why was that? As you can see, our process after exploiting the LDT bug set the root user ID. It set sensitivity label to top secret all, so we had the highest possible sensitivity label in the system. And when a read operation was attempted, our sensitivity label dominated the sensitivity label of the restricted X-type sensitivity label that was assigned to the X-type compartment. So the read operation was accepted, but we couldn't write to that compartment and to its files because our sensitivity label was not equal, because Pitbull requires that whenever a write operation to the object is going to be done, the sensitivity label of the subject and the object itself must be equal. So we decided to set our sensitivity label to restricted X-type to fulfill that requirement for write access. Again, we executed our exploit code. This time as we can see, we had our sensitivity label was set to restricted X-type. We still had access to the index.html file that was the read access, but we couldn't write to the directory of the web pages. The write operation was still denied. And why was that? As we can see, we had root user ID, our sensitivity label was set to restricted X-type. All MAC rules were fulfilled when it comes to read and write access, because our sensitivity label was equal to the sensitivity label of the target object. But according to the DAC, discretionary access control, we were unable to access that object because our user ID was root and the owner of the file was X-type. And according to the DAC mechanism, others didn't have right access to the file. And this is regardless of the fact that we had root user ID, because in Argus Pitbull, root means nothing and is treated in completely other way. So in the next phase, we decided to, that was about 5 AM, we decided to change our user ID to X-type user to fulfill that last requirement. And again, we executed the exploit code. And this time, as you can see, we gained write access to the index.html file. We are able to write to it. So the final goal of the contest was achieved. And we simply changed why it was achieved, because our user ID was with accordance to the DAC access control mechanism, as well as our sensitivity label was with accordance to the MAC access control mechanism. We had the same sensitivity label as the target object which we wanted to modify. Additionally, because we only granted ourselves the access to one of the web pages companies, we wanted to grant ourselves the access to the other one. So we decided to also set all process privileges to the maximum available in the system. We again executed the exploit code. As you can see, we didn't change anything apart from the process privileges. And after executing a command shell, there were several privileges that remained because Pitbull Foundation removed some of the privileges upon the exec system call. But what is important, we had the PV root and PV sub privilege, and that privileges allowed to bypass all MAC and DAC access restrictions in the system. So we were user root, we were having sensitivity level public webhook, but we were able to gain read and write access to any file in the system with the use of the privileges. And we use that to change the web pages of those two fictional companies. We changed them to something like this. And after changing the web pages, we of course informed Argus systems about that. We thanked on these web pages all our competitors for cooperation. And I guess this is all as for the reconstruction of the events from that day. Now I will pass the voice to Michał, and he will try to give you some technical details regarding the exploit code for the LDT vulnerability.
Okay. In this part of our presentation covers some more technical details about exploitation of LDT kernel vulnerability and its application to Argus challenge. Now we'll present some elements of kernel memory protection, and we'll try to describe how Pitbull is integrated with Solaris kernel. Then we will discuss the detailed aspects of exploiting LDT vulnerability and its practical consequences in this specific case of bypassing security mechanism of Solaris enhanced with Pitbull Foundation product. I do not think that I have to convince that the most important part of operating system is its kernel. Users' applications can get access to various kernel components like virtual file systems, kernel services, or networking, only through system call interface layer. Although we do not have access to the source code or design documentation of Pitbull system, we think that we understand the way it works. However, we are fully aware that we did not have enough free time or motivation to go deeper into its analysis. After some reverse engineering, we can assume that Pitbull is integrated with Solaris kernel, at least at the system call interface layer, with possible close and direct cooperation with some components of the kernel. Because interface between user and kernel is clearly defined, it is the best place to create ideal security solution covering all operations which may be initiated by users. In order to better understand the following issues, it is necessary to explain the address mapping for process virtual memory. The most important thing is that there are no separate memory contexts for user and kernel. Therefore, regardless of whether process executes the code located in user or kernel space, it operates on the same virtual address space. The whole memory is divided into maps dedicated to such blocks like kernel data, kernel code, user shared libraries, heap, executable data, executable code. But there is always a clear distinction defined between user and kernel maps. It has great consequences for memory management and overall system speed, as no additional context switching is required. Accesses from user to kernel and kernel to user memories are also significantly simplified. Now we can move to some important memory protection details. Because the operating system kernel contains the most critical data and code, it has to be strongly protected. Such protection is realized by the means of controlling access to memory pages mapped to kernel space. This mechanism is supported by processor, which can operate at 4 different protection levels, where 0 is the most privileged one. Memory accessing in Intel processors is implemented with the use of segment selectors. These selectors represent segments which reflect separated parts of logical memory, address space. For every segment, there is a special descriptor containing segment details such as its base address and limit. Access to segments is defined by descriptor privilege level field. It defines from which protection level a given memory segment can be accessed. This is at least how it can be used. However, it is not, as Solaris does not use the capability of protection at the segmentation level. Both code and data descriptors of kernel as well as user cover the all virtual memory space, which is equal to 4 gigabytes. The actual protection of memory in Solaris operating system is made at memory paging level. The memory pages of the kernel are marked so that can be accessed only from the most protected processor level. As we already said, kernel structures and code are protected from modification or even any direct access from user level. Yet, in order to make the system usable, the kernel provides some services, for example, system calls. This is done with the use of hardware processor mechanisms for transfer control from less privileged, that is user, to more privileged, that is kernel processor levels. The call gates are an example of such a mechanism. The call gate mechanisms allows to add special entries to local and global descriptor tables. These entries are called call-gate descriptors, and they enable transfer control between different segments. The LDT and the GDT tables are special segments where descriptors for all segments of a given process are stored. In order to use the gate, for inter-segment call instruction must be executed with a segment selector of a given gate descriptor as a parameter. Processor finds target segment selector and then segment descriptor, transfers control to it at offset address specified in gate descriptor here, and initiates execution of a procedure. Obviously, LDT and GDT tables are protected from modification from applications executed in user mode for security reasons. However, many x86 operating systems support addition of new segments to local descriptor table. In a Solaris case, this can be achieved with the use of sys-i86 system call. This is the actual point where the discussed vulnerability exists. Security verifications performed in this system call are insufficient, and it is possible to create the descriptor targeting kernel code segment which may be accessed from the user mode. This is caused by the fact that DPL of destination segment descriptor is not checked. Due to this error, it is possible to jump to any address inside kernel space and will result in a switch to the highest processor protection level, which is 0. The presented C language sequence installs fake call gate with kernel code selector as a target. This call gate will be accessible from user mode. After jumping through such a call gate, the system will crash. This is because specified destination address is not valid at this moment. Obviously, this was not our goal. Our goal was to bypass security protection of Solaris enhanced with Pitbull Foundation, not to crash it. At the beginning, we thought that the easiest way to do it would be to jump to existing kernel routines. However, this method turned out to be difficult to complete. So we decided that it would be much more flexible to execute our own piece of code in the kernel space. We have found a method to achieve that. To do it, we make use of the fact that while a jump through call gate is executed, a desired number of parameters may be copied from user to kernel stack. Using this method, we could put 31 4-byte words on the kernel stack. So the only problem was how to find the address of the stack in kernel memory, as it is different for every process. We finally established a way of calculating this address as a sum of stack pointer value obtained with getContext system call and several data values from the stack, values that were put there after a jump through fake call gate. On this slide, there is a piece of code, assembly code, from where the call gate is actually accessed here, and other piece of code that is executed inside kernel on 0 protection level. It is that NOP instruction followed by a long red instruction which is responsible for correct return to user level. However, it turned out that all efforts put in precise copying and jumping to code located at random position inside kernel space are needless. This is because the kernel segment selector covers the whole 4 GB of virtual address space, and therefore also the whole user space. Because after jump through call gate, processor is switched to the most privileged level, it has access to all memory pages. Thus, it is possible to make jump to the kernel code segment to the virtual address taken from user space, where earlier prepared assembly routine could reside. Let me remind you that address of a table with assembly component is known at the time of program compilation. Now it is time to explain why the possibility to execute code on zero protection level is equal to performing any action in a target system. This is because we break protection, software and hardware enhanced, of the most critical part of operating system, its kernel. If integrity of operating system kernel is violated in classical Unix, there are no additional mechanisms which can protect the system from a compromise. And what about trusted operating systems like Solaris enhanced with Pitbull products? The situation is basically the same. The Pitbull extends Solaris operating system with very sophisticated security mechanisms like mandatory access checks to all system resources, for example. However, Pitbull is built upon the assumption that kernel is secure. It does not have any mechanism that would protect its integrity against modification performed at the system kernel level. Thus, Pitbull is effective against attempts to exploit user-level vulnerabilities. It is practically defenseless in the context of kernel-level vulnerabilities. While operating at the kernel level, there are a lot of methods for bypassing additional protection. During the challenge, time was the most critical resource. Thus, we have chosen the most intuitive method based on modification of process credentials. In the first step of this method, we find random memory location where credential structure of our process resides. It can be done by walking through kernel GS segment selector, current CPU structure, and current kernel thread structure. By knowing the address of credential structure, it is possible to modify standard Unix process identifiers, for example, user or group identifiers. Fortunately, it turned out that format of this structure was extended with Pitbull specific fields, such as sensitivity or integrity labels. The first thing to be modified was the user identifier of the process. This seemed to be the simplest thing, as it just required modification of a single short integer value. However, in practice, it was connected with many problems that were due to Solaris support for credential management and sharing. The external modification of real user ID field simply violates integrity of credentials index and leads to the system crash. This is why during the challenge there were some of our processes hanging with modified real user identifier that could not be killed or the whole system would crash. Apart from that, we had to find some way to create a new copy of credentials, so the modifications done to the cred structure would refer only to the single process, our process, not all processes sharing that cred structure. This problem has been solved by executing set user ID system call. The final modification of user identifier was done by setting the effective user ID field of the cred structure. So after modifying Unix credentials, the next step was to modify the Pitbull process credentials. We started with changing sensitivity label structure. Setting classification was simple, as it required only modification of single structure field. However, because assigning user to different compartments was rather complex task in assembly language, it requiring setting appropriate bits in compartment table, we developed a method based on creating completely new as a sensitivity label structure in a C language, and then only copying it with assembly component. This was the final method for modifying process-effective sensitivity labels. Because in Pitbull, process-effective sensitivity label should dominate process minimum clearance and be dominated by process maximum clearance, all sensitivity labels, not only the effective one, were set to the same desired value.
Working on the LDT proof of concept code for SCO, OpenServer and Unix server systems, we have found that there exists a very similar security vulnerability to the LDT one, and it is also kernel level vulnerability. Its impact is that it allows a user to execute code on the kernel level at zero protection level of a processor. And this vulnerability stems from the fact that on SCO OpenServer there exists a system call, the set context system call, which doesn't properly check whether a user sets CS segment coder register of a given process. So a user can set a CS segment coder register to an arbitrary value, for example, to the value of a kernel code segment, and by doing this, he can pass execution to the kernel level. We have informed Caldera systems about this vulnerability. We have received today information about that they have prepared fixes for this one and also for LDT vulnerabilities for Unix and OpenServer. And as they said, these fixes are already available. So we've come to the conclusions of the presentation. So I hope that the presented material was a good example of how complex some modern security mechanisms could be, and also how complex must be appropriate attack techniques that bypass such mechanisms. Also, we hope that we prove that there isn't such a thing like completely secured system. And what was also a goal in this presentation was that to show you the practical impact of kernel level vulnerabilities and how great that impact might be for the security of systems, because we are used to user level vulnerabilities to format string, buffer overflows, etc. But there exist kernel level vulnerabilities, and they might have very dangerous impact on the security of the systems. When it comes to our gains and losses, so without any doubt, attending this hacking challenge, it was definitely an interesting experience, and it was a possibility to participate in a great event. It was also an opportunity for us to meet some interesting people, as we've been put for some period of time into a spotlight after winning the challenge. And obviously the prize money was also very attractive for us, but it hasn't been paid up to this day, but only partly paid. For Michał, it was an unforgettable bachelor party, as he was getting married a week later. When it comes to disadvantages, of course, that was a long, sleepless night, hard-working night. We've drank 16 liters of Pepsi within 24 hours, and that, of course, isn't very healthy. And after the challenge, we had some opportunities to meet, maybe not very often interesting journalists, but to meet with journalists at all. So I would like to thank you for attending our presentation, that you stayed up to its finish, and I should say that this presentation is based upon the technical article that we wrote about the kernel level vulnerabilities, about the August challenge thing, It is 70 pages long. It will be available within days on our website, along with this presentation, so you can go there and download all this stuff. I can assure you that you will find a more detailed description of the whole event and the more detailed description of how we exploited LDT vulnerabilities on every vulnerable system. Also, proof of concept codes for every vulnerability will be available on our website. That will be within days after we come back to Poland from Amsterdam. So thank you for your attention, and I hope that in this presentation we showed you a much more friendly face of Pitbull. So thank you. If you have any questions, you can ask them now or yes, please.
Have you compared Pitbull to the SE Linux prototype project? The features seem to be almost identical.
Could you repeat that Linux project?
There's a Linux project from the NSA, which is called SE Linux, or Secure Linux, which is essentially the same with Mac control and stuff like that.
Chcesz porównać?
Powiedz, że znamy jak działa ten system Linux, natomiast nie dokonywaliśmy takich porównań.
Okay. Michael was looking into this system, but we can't compare it with Pitbull, as that wasn't much a deep look, so can't help you here with any comparison. Maybe some other question? If you want to get in touch with us, here you have our mail address. You can, of course, get with us after this presentation here. We will be available for a couple of minutes. Or to the end of the conference, I think that we'll be wandering around here somewhere. Okay, thank you.